Welcome to this video on free energy changes. We're going to look here at how the free energy enables us to determine whether a reaction is feasible. So far in this topic we're going to be looking at this fundamental question of how we decide whether a chemical reaction is going to happen, and we've introduced this concept of feasibility to help us to do that. And what we've done is that we've looked at some different reactions. So for example, water boiling. At the moment, water boiling is not going to be a feasible process. We don't see water boiling at 25 degrees C at least. And we looked also at the enthalpy and entropy changes for that process, and we found that this is an endothermic reaction. It makes the surroundings colder, but the entropy change in this case is going to be positive. So it's endothermic with a positive entropy change. Vinegar and bicarbonate of soda, as you can see from this picture on the right hand side, it definitely is a feasible reaction. That one is actually, perhaps surprisingly, an endothermic process, and it has a positive entropy change. The hydrogenation of benzene was another process that we looked at. That's actually an exothermic reaction, and it has a negative entropy change. And in fact that turns out also to be a feasible process. So this leaves us in a little bit of a pickle. If we're trying to predict whether a chemical reaction will happen or won't, we can't just use enthalpy, because we've got here endothermic reaction that doesn't happen and an exothermic reaction that does, but also an endothermic reaction that does. So enthalpy won't work. Entropy, we thought that might be a solution, because the second law of thermodynamics says the entropy has to increase in a spontaneous process or a feasible process. But we've got a process here with a positive entropy change which isn't feasible. And similarly a process here with a negative entropy change which is feasible. So how can we work this out? Well, it turns out that we need a combination of entropy and enthalpy changes, because the second law of thermodynamics states that it has to be the entropy of the universe that increases. And at the moment, this is delta S here is simply telling us the entropy change of the system. And so what we need is a combination of these two which takes account of the entropy change of the surroundings. And because if energy is released into the surroundings by the reaction, then that actually will increase the entropy of the surroundings. So this is somehow here related to the entropy change of the surroundings. And you can go into this and actually show mathematically why this relationship comes about. But it turns out that if you combine delta H and delta S in the following way, you get something called delta G. And that has a very, very simple relationship to feasibility. If delta G is less than 0 for a feasible process. So these are really, really two immensely important ideas to have your head around. This definition of the free energy and this condition for feasibility. Now, final thing I just want to mention before we move off this slide is the numbers that are involved here. So we've got here enthalpy and entropy. We've also got here T, which is the temperature. And that's temperature in Kelvin. And the other thing that we just need to be aware of here as we're working through this is enthalpy change is going to be in kilojoules per mole. And therefore we're going to need to make sure that our entropy change here is also in kilojoules per Kelvin per mole. If this is going to work. And that would give us delta G in units of kilojoules per mole. So let's see how this all works out. Here's an example for you to have a go at. Pause the video and see if you can work out delta G for this reaction here under the conditions shown. Well, let's see how you got on. So again, we're going to use our classic relationship. Delta G is delta H minus T delta S. So first situation here, we've got, if we're going to work out delta G, we need to plug in the enthalpy change, and I always stick brackets around these in order to make sure that I get these right. And it's minus T, which is 298, times delta S, which is going to be minus 118.8. But if we go back to the previous slide, we had to convert that into kilojoules per Kelvin per mole, because otherwise it won't line up with the enthalpy, which is in kilojoules per mole. At the moment, this is in joules per Kelvin per mole. So to turn that into kilojoules, we need to divide the number by 1,000. And so we need to take this number here, and we need to divide by 1,000. So when we do that, it turns out that we get a value of minus 8.6 kilojoules per mole. So we would say here that we've got a feasible reaction at 25 degrees C. Now that, just a couple of pointers. I'm using, in this case, a 1 decimal place answer, because I've got 1 decimal place values here. This would be my, once this is divided by 1,000, this is going to be 4 decimal places. But this is 1 decimal place, which is my lowest number of decimal places, and so that's what I need in my final answer. In this case, because we're adding and subtracting, we conserve the number of decimal places rather than significant figures. So minus 8.6 kilojoules per mole. Now, does that make sense? 298 room temperature, would we expect steam to condense? Absolutely we would. Right, let's go on to the second one. Delta G, again, very, very similar, minus 44. This time the temperature, we've got to turn 125 degrees C here as our value. This, to turn that into Kelvin, we're going to need to add on 273 to give us 398 Kelvin. So we're going to stick 398 Kelvin in there, and again we multiply by exactly the same entropy change, which we're going to divide by 1,000 on the go. And if we stick all that in our calculator, we should get plus 3.3 kilojoules per mole. So we would say at that temperature, this is not feasible. Which makes sense. Above 100 degrees C, the most stable phase of water, at least at atmospheric pressure, is gaseous water. So we're not going to get steam condensing spontaneously to liquid water.